Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we shall be discussing about gravitational field. So relax, do not go anywhere, I'll be right back. You are welcome back to my school YouTube channel. Like I said earlier, we are going to be discussing about gravitational field. So before we begin with our lesson, let's quickly run through the objective for today's lesson. So objective number 1, calculate the gravitational force between two masses. 2, explain the meaning of capital letter G and show that small letter g is the force per unit mass on the Earth's surface. 3, explain the concept of escape velocity. 4, explain how artificial satellites are launched. And 5, distinguish between natural and artificial satellites. So let's kick off with our lesson. So basically here we are going to be looking at the meaning of gravitational field. Now remember that while we were discussing about description of field in our previous video, we did talk about gravitational field. So today we are going into it properly. Okay, so gravitational field is simply defined as a region or space around the mass in which the gravitational force of the mass can be felt. Okay, so a gravitational force exists between a body and other bodies around it. That is, every mass has a gravitational field around it. Okay, so for example, the Earth and the Moon, okay, or the Sun and the night planet. So in this case, the mass here is the Earth or the Sun, while the night planets or the Moon are the other bodies around them. Okay, so let's move ahead and talk about the law of universal gravitation. Okay, so the law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. So the above law is known as Newton's law of universal gravitation. So mathematically, from the law can be stated mathematically as F is directly proportional to the product of the masses of the particles, which is m1, m2, then and inversely proportional to the square of the distance between the particles. Okay, where F stands for force of attraction between the particles or body m1 and m2 are the masses of the two particles or body, while R is the distance between the particles or body. Okay, of course, what we have here is just a relationship, so you cannot really do anything with this. Okay, so in order to be able to make use of this, most especially in calculation, okay, so you have to introduce a constant. So when that constant is introduced, then this symbol of proportionality will now change to equals to, so that F is equals to G, capital letter G, m1, m2, all over R square, where G is known as or is called the gravitational constant. Okay, and its value is, let's move over to the next slide, and its value is 6.67 times 10 raised to power minus 10 Newton meter square per kilogram square. Okay, and its value is 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. So this is just the diagram of the two bodies, and this is the force of attraction between them. Okay, so the distance arrow is measured from the center of one body to the other. So this is exactly what you are seeing on the diagram above. So the force F, which is these forces, is always that of attraction. Okay, and this is the force that keeps the Earth in its orbit around the Sun and the Moon in its orbit around the Earth. So now let's discuss about the relationship between capital letter G and small letter g. Now we've already seen what capital letter G represents. Remember, capital letter G is called gravitational constant. Okay, so as the lesson proceeds, we'll also see what small letter G represents. So basically what we want to do now is to show the relationship between capital letter G and small letter g. So let the mass of the earth be capital letter M, and let the mass of an object on the earth's surface be M. Then small letter m. Let the radius of the earth be capital letter R. Then the gravitational attraction between the earth and the object is given by F is equals to GMM. Okay, remember here we have capital letter G, capital letter M, and small letter m all over capital letter R square. Now, radius of the object is negligible compared to the radius of the earth. Let's move to the next slide. So the weight of an object is the Earth's gravitational attraction, F, on the object. So mathematically, F is also the same thing as weight. Why? Because weight actually depends or is dependent of the Earth's gravitational attraction. So without the Earth's gravitational attraction, there will be no weight. F and W are literally the same and is given as mg, which is m times g, where g is equals to acceleration due to gravity. So small letter g represents acceleration due to gravity. We call this equation 2, while the previous equation, which is F is equals to G, capital letter M, small letter m all over R square, we called equation 1, right? So equating equation 1 and equation 2, we are going to be having GM all over R square is equals to mg is equals to F. So basically here we only need these two formulas, because since they are equal to each other, okay, and also equal to F, that means any two of them can be equal to one another. So we simply divide through by m. Okay, so if we divide through by small letter m, then the small letter m here will cancel out. Then the small letter m here too will also cancel out. Okay, and then this f will also divide it by m. Now the term f over m is referred to as force per unit. Therefore, acceleration due to gravity can be defined as the force per unit mass on the Earth's surface. Now remember that in our previous lesson on description of field, we also defined it as the acceleration of an object due to the Earth's gravitational force of attraction. Okay, so from the above, we can make m, which is capital letter M, which is the mass of the Earth, the subject of formula. Okay, by simply cross multiply. From here, if we cross multiply, we'll be having Gm to be equals to R square G, right? So since we are looking for capital letter M, we simply divide by G. So if we do that, M will be equals to small letter G, capital letter R square all over big letter G. So this is the formula for calculating the mass of the Earth. Also, from the above relationship, we can see that G is inversely proportional to the square of the distance between the mass. Okay, that is G is inversely proportional to the square of the radius of the Earth. Since the Earth is not perfectly spherical, the radius R, capital letter R, varies along the Earth's surface. Let's move to the next slide. Greatest at the equator and least at the pole. Thus, G also varies from place to place on or around the Earth's surface. Least at the equator and greatest at the pole. So here are some work examples for us to apply some of all those formulas we have seen, okay, so that we know how to use those formulas in solving problems. So let's begin with question 1. A body moves in a circular orbit of radius 4r around the Earth. Express the acceleration of free fall due to gravity of the body in terms of g. So here we are asked to take r, which is capital letter r, the radius of the Earth, and g is equals to acceleration of free fall due to gravity on the Earth's surface. So to solve this, we have to move over to the board to provide answer to this question. Okay, so the essence of these examples is so that we can apply, or we can see how we can use those formulas in solving simple problems. Okay, so in this question, basically we are asked to express the acceleration of free fall due to gravity of the body in terms of g. Okay, so in this case we say let the acceleration due to gravity of the body be given as g prime, right? So if it's given as g prime, we know that this will be equals to gm, okay, all over r. right? So this is the acceleration due to gravity at a point r from the surface of the earth. But remember that acceleration due to gravity on the surface of the earth is given as g is equals to gm all over r. So just take note of this. But in this question, we are given r, which is the radius of the body, okay, that is moving in a circular orbit, to be equals to 4r. So in this case, our r is equals to 4r. So anywhere we see r in this expression here, we are going to replace it with 4r. So our g prime now becomes gm all over 4r, right? Now this our g prime, we can rewrite it as 1 over 4 times gm all over r, right? We can rewrite it as gm all over r. Our r here is squared, okay? So our r here is squared. So if we do that, here we'll be having squared, right? So this will be equals to gm all over 16 r squared, right? So we can rewrite this to be equals to 1 over 16 times gm all over r squared. But remember that gm all over r squared is equals to g, which is acceleration due to gravity on the surface of the earth. Now remember, in this question we are asked to solve it in terms of acceleration due to gravity on the surface of the earth. So anywhere we see gm all over r squared, we replace it with g, so that our g prime is now equals to 1 over 16 times g, which is the same thing as g all over 16. Okay, so the acceleration of free fall due to gravity of the body in terms of g is equals to g all over 16, or 1 over 16 times g. So let's return back to the screen to continue with the remaining example. So let's move on to example 2. A man and his friend have masses 70 kg and 60 kg respectively. If they are seated 1.0 meter apart, calculate the gravitational force of attraction between them. Okay, so let's move over to the board to provide answer to this question. So let's move over to the board to provide answer to this question. So in this question, we are simply asked to calculate for the gravitational force of attraction between a man and his friend, right? And their masses were given to us. So let's say the man be m1, so that will be 70 kg, and his friend m2, that will be 60 kg, right? But remember that the force of gravitational attraction F is given as g, then m1, m2 all over r squared, which is the distance between both of them. Okay, so here F will be equals to, of course we know this to be 6.67 times 10 raised to power minus 11, then times the mass of the man and his friend, which is 70 times 60, then all over r squared, which is the distance between them. Now remember that in this question, it is given to be equals to 1 meter. Okay, so in place of r here, we just put 1 meter, which will give us 1 square, and 1 square still remains 1. Okay, so now this is what we do. Now, first of all, we are going to eliminate this decimal point so that we can be able to multiply without any difficulties. So to eliminate this decimal point, we just move it 2 times to our right. Okay, so if we move it 1, 2. So since we move this 1, 2, since we move the decimal point 2 times, we are going to subtract minus 2 from here. Now remember that if you are moving decimal point from your left to your right, you are going to subtract from the power. Okay, but if you are moving from your right to your left, then you are going to add to the power. Okay, so in this case, we are having 667 times 10 raised to power minus 13, then times, so if we multiply these two, definitely here we are going to be having 42, then times 10 raised to power 2. So that should give us like 4,200, right? Now divided by 1. So anything divided by 1 still remains that. So let's deal with this first. So if we multiply these two, we are going to be having 28,014. Then times, of course, here we can apply the law of indices. So here we'll be having 10, then minus 13, then plus, since we're multiplying, plus 2. So at the end of the day, we'll be having 28014 times 10 raised to power minus 11. Okay, but then we don't stop here because this must be in standard form. This is not in standard form. So in order for us to bring this in standard form, there's an invisible decimal point here. So we have to move it, okay? We have to move it to our left. So we move 1, 2, 3, 4. So we'll be having 2.8014 times 10 raised to the power minus 11. Now remember that we move the decimal point from our right to our left. So in that case, we are going to be adding. We moved it 4 times. So you'll be having plus 4. Okay, so minus 11 plus 4, that will give us minus 7. So at the end of the day, our F is equals to 2.8, let's just leave it here, or 0.80 times 10 raised to the power minus 7 Newton. So this is the force of attraction between the man and his friend. So let's return back to the screen so that we can answer question 3. So question 3, if the distance between two equal masses is doubled and their individual masses are also doubled, what would happen to the force between them? So let's move over to the board to provide answer to this question. So let's return back to the board to provide answer to this question. So in this question, we are told if the distance between two equal masses is doubled and their individual masses are also doubled, what would happen to the force between them? Now remember that in this question we are told that the masses are equal, right? So remember F is equals to G m1 m2 all over r squared, right? So before their masses were doubled. Now since both masses are the same, so we just say m should be equals to m, right? Since both masses are the same. So since both masses are the same, and here we are having multiplication, so we just multiply them. So that we'll be having m squared, right? So F for the initial force of attraction between the masses will now be equals to G m squared all over r squared. Now the final force, let's see what will happen if the masses are doubled and the distance between them is doubled. So if the distance between them is doubled, that means r is now equals to 2r, right? Then remember m will now be equals to 2m because it's double. But since the masses are equal, that means we're having 2m to be equal to 2m. So if we bring that here, so we'll be having g, then that will be 2m in bracket square, okay, because they are multiplying, the two masses are multiplying each other, all over 2r in bracket raised to power 2, right? So here we'll be having g, then we'll be having 4m square all over, because this 2 is affecting everything inside this bracket. So this will be 2 square and m square. So 2 square is 4 and m square is m square, right? Then or m square is equal to m raised to power 2. Then here is still the same, we'll be having 4 then r square, right? So 4 we cancel out 4. So at the end of the day, the final force is equals to g m square all over r square, which is also equal to the initial force of attraction between the body before their masses were doubled and the distance between them were doubled. So even though the masses were doubled, right, and the distance between them was also doubled, the force of attraction between both masses still remains the same. The initial force of attraction between the two masses is also equal to the final force of attraction between the two masses. Okay, so let's return back to the screen to continue with our lesson. So let's move to the next slide. So on the next slide there, we are going to be discussing about the variation of G with altitude or height, right? Of course, we've already shown this mathematically in the previous slide. So, but let's just go through it for more emphasis. Okay, the acceleration due to gravity at the surface of the Earth is given by G is equals to G, that is capital letter G, capital letter M all over capital letter R square. Now remember, R here stands for the radius of the Earth, capital letter M here stands for the mass of the Earth, and G stands for gravitational constant. Okay, so we'll call this equation 1. Now the acceleration due to gravity at a height h above the surface of the Earth is given as G prime, just like the example we just the example we just saw. Okay, G prime equals to Gm all over arrow plus h, right? So arrow here is the radius of the earth, while h is the distance of the object, okay, from the surface of the earth. So to get the whole radius, you have to add both of them together. Okay, so that arrow is now equals to capital letter R plus h in bracket square. Okay, so we call this equation 2. So dividing equation 2 by equation 1, we'll be having G prime all over G is equals to arrow square all over arrow plus h in bracket square. So we call this equation 3. Okay, so basically let me just show you what happened here. So we divided G prime by G, so this will be G m all over arrow plus h in bracket square. So since we are dividing, we just invert, so you'll be having times arrow square all over gm, right? So gm will cancel out gm, and that's what resulted to this. Okay, that's what resulted to this. So the term arrow square all over arrow plus h in bracket square is less than 1. Okay, therefore g prime all over g is less than 1. So if we cross multiply, we'll be having that g prime is less than g. So this means that the acceleration due to gravity decreases with increasing altitude or height. So this is where we draw the preview of today's video lesson to a close. I hope you enjoyed it, but you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you will learn about gravitational potential, gravitational field intensity, you learn about weightlessness, and you will also learn about escape velocity with work example and many more. So I believe you enjoyed the preview of the video that you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly tap on the notification bell to get informed as soon as we release the next video.